There are so many hidden facts, hidden concepts inside the empirical formula that many of us were not exposed to in secondary school. So sit back and watch us unfold the hidden facts in empirical formula. Now, empirical formula is the simplest formula of a compound that shows the relative mole ratio of the elements present in the compound. All right. Now, I repeat, empirical formula is the simplest formula of a compound that shows the relative mole ratio of the elements present in the compound. All right. Now, molecular formula is a formula that shows the actual number of atoms of each element. Now, empirical formula only tells us the ratio in which the elements are being combined. It doesn't tell us the actual number of atoms of each element. But molecular formula is a formula that tells us, that shows the actual number of atoms of each element present in the compound. I give us a typical example. Look at these few examples. I just want to use this example to explain so that we understand how empirical formula differs from molecular formula. So you don't just have to, jump on concluding that questions on the empirical formula is always based on calculation. Now remember, I just told us now that empirical formula only shows us the ratio of the element that is being combined. Now let's look at this first example. We have C6H12O6. There are three elements present in this compound. We have carbon, we have hydrogen, and we have oxygen. Three elements. Okay. Now you ask yourself, can this compound be broken down further? Can we reduce this guy to the barest minimum? Yes. Now, what can go into 6, into 12, and into 6? Of course, 6 can go into itself, 1. 6 can go into 12, 2. 6 can go into itself, 1. So this becomes the empirical formula of this compound, which means that this compound is a molecular formula. Right? Now, this is the empirical formula of this compound. The ratio of the elements are in a ratio of 1:2:1, corresponding to what I told us earlier, that empirical formula, right, shows the ratio of the elements. And here we have three elements: carbon, hydrogen, and oxygen. Now let's look at the next example. We have C12H22O11. Now this cannot be broken down further because these numbers, no single whole number can run through these 12, 22, and 11 without any remainder. Okay, now 2 can go into 12, 6, 2 can go into 22, 11, 2 cannot go into 11. We are looking forward to break it down so that we're not going to have any remainder. So for the fact that we cannot break this guy further than this remains as empirical formula and also doubles as a molecular formula. There are cases where the empirical formula would be the same thing as the molecular formula. And here is an example of such. Okay. So this is an empirical formula because this cannot be broken down further, and this also doubles as molecular formula of this compound. Now let's look at the fourth guy. We have P4O10. Now, what can go into 4 and go into 10 without any remainder? 2 can go into 4, 2 can go into 10, 5. It means that this compound is actually not empirical formula. This is actually molecular formula because this can be reduced further. All right. So if you break this guy further, this becomes the simplest. It cannot go beyond this. So this is actually the empirical formula, and this is the molecular formula of this. I believe you understand how we're making progress, because empirical formula says it is the simplest formula, whereas molecular formula is a formula that tells us the exact number of atoms of each element. So here we have 4 atoms of phosphorus, 10 atoms of oxygen. All right. Here we have 12 atoms of carbon, 22 atoms of hydrogen, 11 atoms of oxygen. However, this compound turns out to also be the empirical formula. Now let's look at the last one here. Now, NaAl3F6. Now this is actually an empirical formula and also a molecular formula, because we cannot break this guy further than this. Remember, we are looking for a number that will run through these three values. Apart from 1, you cannot use 1 to divide through, because anything divided by 1 is still that same value. Right? 3 can go into itself 1, 3 can go into 6, 2, 3 cannot go into 1. Right? It means that this is the simplest form this guy can take. So which means this is the empirical formula, and this is also the molecular formula of the compound. So take note, empirical formula can also double as a molecular formula if that formula is written in its simplest form and also carrying the actual number of atoms of each element. All right. So the next example we're going to do now is to look at the calculation aspects in empirical formula. Remember, many of us before now were not aware of this. All you just know is to just jump into calculation of empirical formula. But with this now, you've actually understood that apart from the calculation aspects, we also have other aspects of empirical formula. So we're going to look at the calculation aspects. A compound contains 54.82% of carbon, hydrogen, 7.10% of nitrogen, and 32.46% of oxygen. Now, if you notice something here, they did not give us a percentage of hydrogen. Okay, they only gave us a percentage of carbon, nitrogen, and oxygen. And we are asked to solve for the empirical formula. Now, what you're simply going to do here, in cases like this, since the composition of the compound, remember, a compound must always contain elements, right? We are being told that this compound contains carbon, it contains hydrogen, it contains nitrogen, it contains oxygen. Now, the composition of this compound is given to us in terms of percentage. Okay, now they told us that percentage of carbon is 54.82%. They did not give us that of hydrogen. That of nitrogen, they gave us to be 7.10%. That of oxygen, they gave us to be 32.46%. Now, what exactly are you going to do here? Very simple. Now, since the composition is given to us in terms of percentage, and we all know that anything that is actually given to us in terms of percentage, the total should always round up to 100, right? Now, so for us to find the percentage composition of hydrogen, we are simply going to add up the percentage composition of that of carbon, that of nitrogen, and that of oxygen, and subtract it from 100, because 100 is a total percentage that a compound is going to have, so long as they give us others in percentage. So hydrogen is going to be 100 minus that of carbon is 54.82 plus that of nitrogen is 7.10 plus that of oxygen is 32.46. Now the answer here becomes 5.62%. So you can see that the percentage of hydrogen is now 5.62. How did we get the 5.62? You add up the percentage of this. Now this adding up and subtracting from 100 is only done when the composition of the compound is given to us in terms of percentage. Okay? All right, so let's proceed. Now, we've gotten the percentage of carbon, hydrogen, nitrogen, and oxygen. Recall what I told us earlier. If you want to solve for empirical formula, you have to first of all put out the elements first so that we know the element that are present. Now, what we are looking forward to get is the ratio in which this element is going to combine with this in that compound. That's the ratio is what we're looking out for. So this percentage by mass is always written here. There are cases where empirical formula, the composition will not be given to us in terms of percentage. They will just give us mass. There's no problem. You're still going to maintain the same pattern to solve. Now, this is step one. Step one is to divide by the molar mass of each of the respective elements. Molar mass of carbon is 12. So I'll say step one, divide the mass of carbon by its molar mass. So divide by their molar masses. You might want to call it atomic masses. So this becomes 54.82 divided by 12. Now this is 5.62 divided by 1 because the molar mass of hydrogen is 1.008. So you can just approximate it to 1. Nitrogen is 14. Atomic mass of a single nitrogen is 14, right? And that of oxygen is 16. Since oxygen here is just a single atom. Okay, I already solved this, so I will just put out the values. So this will give us 4.57. This will give us 5.62. This will give us 0.51. This will give us 2.03. Okay, so our step 2 is to look for the smallest amongst all of them. Use that smallest value to divide through. So if you look at the answers we got from this, 4.57 for the first one, 5.62, 0.51, 2.03. Now this 0.51 turns out to be the smallest amongst all of them. So we're going to say step 2 would be divide through by the smallest. Now when you do that, this becomes 4.57 divided by 0.51, 5.62 divided by 0.51, 0.51 divided by 0.51, 2.03 divided by 0.51. So this will give us 1. This will give us 4, approximately 11, and 9. So therefore, the empirical formula of this becomes C9 H11 N NO4. Now this becomes the empirical formula of this compound. Now carbon, hydrogen, nitrogen, oxygen are combining in this ratio. 9:11 to 1:4. As simple as that. Now you can actually want to go through this again. The first thing is for you to put down the percentage by mass. In some other cases, they will just give you the mass, not in percentage. The same process is what you're going to do. Put the value down. Now divide by their molar masses or the atomic mass. Carbon has a molar mass of 12. Hydrogen has molar mass, atomic mass of 1. Nitrogen has 14. Oxygen has 16. Okay. Now take note that this nitrogen is a single atom, not a double atom. Take note of that. In empirical formula, we are dealing with single atoms, right? The molar masses in empirical and molecular formula are just the molar mass of the single atom, since it is the element we're interested in. So this is how we got this. Okay, we have another question here. They said 2.5 grams of a compound containing only phosphorus and chlorine. 2.50 grams of a compound containing only phosphorus and chlorine was analyzed to contain 1.94 grams of chlorine. What is the empirical formula of the compound? Now, this particular question is very similar to the first one we did. However, the nature of the question in terms of the value seems to differ. Now, this is actually given to us in terms of mass, not in percentage as they gave us in the previous example. And here they gave us the total mass of the compound. All right. Now, for us to solve this, I'll say solution. Okay. Now, total mass is equals to mass of phosphorus plus mass of chlorine. Now, the total mass of the compound they gave us to be 2.50 grams equals to mass of chlorine. Mass of phosphorus was not given to us. So I'll say mass of phosphorus is X plus mass of chlorine they gave us to be 1.94. So the reason why they gave us this total mass is for us to be able to use it to get the mass of the phosphorus that was not given to us. So obviously this becomes mass of phosphorus now becomes, if this comes over, we have 2.5 minus 1.94. Now this is equals to 0.56 grams. So therefore, we now have the mass of phosphorus to be 0.56 grams. We have the mass of chlorine to be 1.94 grams. Now, we have no business with the total mass again. The sole aim of this total mass was for us to be able to use it to get the mass of phosphorus. Right? Now, let's dive into our solving proper. Okay, now we've gotten the mass of phosphorus, we've gotten the mass of chlorine. Now step one is divide each of them by their respective molar masses. Divide each of them by their respective molar masses. The molar mass of phosphorus is 31 grams per mole. The molar mass of chlorine is 35.5. So I would say this divide by 31. Okay, step one is, let's say, step one, divide each by their molar masses. So this becomes 35.5. So if you divide this, we're going to have 0.018. We're going to have 0.055. Now recall, once you're done with the step one, the next thing you're going to do is to look at these two answers. Which of these two guys is the smallest? Whichever of them is the smallest, you're going to use it to divide through. So divide through by the smallest. So step two, divide through by the smallest. So this becomes 0.018 divided by 0.018, 0.055 divided by 0.018. Now this is 1 and this is 3. So therefore, phosphorus is 1 and chlorine is 3. Now this becomes the empirical formula of the compound. You can see how simple that is. So we have this question here. The compound contains 38.72% of carbon, 9.65% of hydrogen, and 51.63% of oxygen. If the molecular weight of the compound is 62 grams per mole, what is the empirical formula and molecular formula of the compound? Now, solution. I'm just going to go straight to solve for the molecular formula, so the empirical formula, since I've done the previous explanation and the previous examples. So we have its percentage, we have carbon, hydrogen, and we have oxygen. Carbon is 38.72, 9.65, and 51.63. Now please always endeavor to add up these values to ensure it gives us 100. Okay? Now remember our step 1 is to divide by their respective molar masses. So divide by 12. divide by 1 and divide by 16. So this becomes 9.65. This becomes 3.23. It becomes 3.23. Now the next thing is for us to divide through by the smallest. Right? Here, divide through by the smallest. Divide through by the smallest. Now this becomes 3.23 divided by 3.23, 9.65 divided by this. Now this is 1, this is 3, and this is 1. So therefore, our empirical formula becomes CH3O. That is our empirical formula. Right, carbon is 1, the ratio is 1:3:1. So, but remember they told us to solve for empirical formula and molecular formula. So we've gotten our empirical formula. Now, it's important for us to know that even if they did not ask us to solve for empirical formula, if they had asked us to solve for molecular formula, you must get empirical formula first before you proceed to solve for the molecular formula. So this is just for formality. Even if they had not said solve for the empirical formula, I would have still solved for empirical formula, because for me to solve for molecular formula, I need to know my empirical formula. Okay? So let's molecular formula, we want to solve for the B. Molecular formula. Now molecular formula, let's call it MF, and let's call empirical formula E.F. So molecular formula is equals to empirical formula subscript N. Now this N is always what we call, it has a formula of molecular weight slash or mass all over. Please, this E.F is empirical formula weight, right? Just to save time and to save space. E.F empirical formula weight, molecular weight. All right. Now, what is N? N is actually a whole number multiple. N has to be a whole number, right? This is what differentiates molecular formula from empirical formula. Now, for us to solve empirical formula, or for us to solve molecular formula, we need our empirical formula, right? And we need to solve for this N. How do we solve for the N? That is what I'm about to show us now. The molecular weights, it will always be given to us in the question. They said, if the molecular weight of the compound is 62 grams per mole, so it means that they have given us our molecular weight to be 62 grams per mole. How do we solve for empirical formula weight? They did not give us this in the question, but based on our empirical formula calculation, they gave it to us. So empirical formula was CH3O. Now, what is the weight or what is the mass of this? Now, the molar mass of carbon is 12 plus hydrogen is 1, but hydrogen is appearing 3 times, so I say 1 times 3 plus oxygen is appearing once. Now this is 12 plus 3, that's 15, plus 16, that is 31. All right, now empirical formula weight is very simple. Calculate for the molar mass of the empirical formula. Take into consideration their atoms and how many, their elements and how many times they are appearing. Carbon is appearing once, 12 times 1 is 12. Hydrogen is appearing 3 times. Molar mass of hydrogen is 1. 1 times 3 is 3. Molar mass of oxygen is 16. 1 times 16 is 16. All right. So we'll come here. We'll say the molecular weight of the compound was 62. Our empirical formula weight is 31. So our N becomes equals to 2. Can you see that? So therefore, our molecular formula is equals to empirical formula subscript N. So I'll say E.F What is our E dot F? CH3O. What is our N? 2. So this becomes 2 into 1, right? This 2 is going to expand the brackets. This is C2H6O2. So that is the molecular formula of the compound. So for us to solve molecular formula, you need to take this into consideration. Molecular formula is empirical formula times N. You must always solve for this. And N is always molecular weight of the compound. Most of the times, weights and mass can be used interchangeably. All about the empirical formula weight. I just showed us how to get the empirical formula weight. Now, put it here, divide the molecular weight by this. You get your N. You come back and put N to be equal to 2 here. After you must have inserted our empirical formula. So this becomes our molecular formula.